Okay, so let me say that only 3 of you have turned in homework 2, which makes me very happy because I'm not finished grading homework 1 yet. So thank you for that. The next homework I will probably post on Monday. That's my guess. So if you're behind on homework 2, you are forgiven, right? Just get it to me as soon as you can. Okay, questions? Okay, so let's kind of pick up where we left off. The last thing that we had is this big connection with integrality and this module condition, right? U is integral essentially if and only if there's a finitely generated submodule TA such that UA is contained in A. So let's get to it. Theorem 314. Of rings and S and T and S. If S and T are integral, over R, then so is S plus T and S T. If you remember from back in the day, when you did like maybe field theory, this is very similar to the kind of the same idea with algebraic, right? At some point we'll probably prove that if S and T are algebraic, these are field extensions, then the sum and the product are still algebraic, right? And so prove that let's say A, the module for S and B, the module for T. So I'm kind of sketching out why this is true. No, that is to say, SA is in A and TB is in B, and A and B are finitely generated. So they're finitely generated R submodules B. Then note AB is also finitely generated. In fact, if A is generated by A1 up to AN, and B is generated by B1 up to BM, then AB is generated by all possible products of those, right? And of course, the products make sense because these are submodules of T. Right? Note also that if you look at ST AB, this is contained in AB, right? Because the SA business is in A and the TV business is in B, right? And by again the same sort of logic, because every SA is in A, and so that's still in AB, and every TD is in B, yeah, still in there. So this actually shows what we wanted. So this is actually, I mean, I haven't really thought about this, but it might be interesting to see how one would try to proceed from only the polynomial definition, right? I mean, how would you actually produce a polynomial, right? The one for ST, the one for S plus. Corollary. This morning. Clear. And I'm going to use this corollary actually to introduce a little bit of notation here. let R be a, let R inside P be an extension of the ring. Then I'm going to define this. So R sub T with a little bar over it. This is the set of T and T such that T is input over R. This is a subring of T containing R. Okay, so let me just make sure that I at least kind of hit the main points of this. Well, first of all, by definition, this is a subset of T, right? Because I'm only taking the elements T and T that are integral over R. RT is closed under addition and multiplication by theorem 3.1. Right. And so this is like a ring. It's actually closed under subtraction as well. It's fairly easy to see that S is integral and negative S is integral as well. In fact, for that one, you can explicitly write the polynomial, given the polynomial for S. And so it's a ring, it's contained in T, so there we go. And now containing R is all we need. R is in R, then, well, it's T, then R is a root of the monic polynomial X minus R. So that shows that it contains R. Everything in R is in. Okay. Definitely. Ring is called the integral closure of R in T. So the set of everything in T that's integral over R is called the integral closure of R and T. If R is a domain and K is the quotient field of R, then this is the integral closure of R in its own quotient field. Sometimes we suppress the K when so we suppress the K actually in this context, and this is called the integral closure. So this is just the set of everything that's integral over R and is also in the quotient field of R. If R then R is integral closed. If R is equal to its own interval closure, then it is called an interval closed ring. What other definitions I want to throw in here? And of course, I think this is a repeat, but if every element of T is integral over R, then we call T an interval extension. So I can put that in terms of its notation. If everything is integral over T, if everything in T is already integral over T, then T is an interval extension. Now, at this point, I think it would probably behoove me to do some examples. Z inside Zi is an interval extension. We've done this example before, but I want to emphasize that this is not the integral closure. This is Zi, in fact, is the integral closure of Z in the field Qi. Because notice that Z and Zi have different quotient fields, right? I is not the quotient field of Z, it's not big enough, right? Z itself, so that's an integral extension. Zi is integral over Z. Z itself is integrally closed. So let me review what that means. That means that every rational number that is the root of a monic polynomial over Z, the only ones are integers themselves. Let's prove that as part of this example. Claim that Z is interval closed. Now let's see what that's true. Let's suppose A over B and Q is interval. Over Z. So suppose I have some fraction that is the root of some monic polynomial called Z. Now, there's no harm in assuming the following. Without loss of generality. By the way, I hate this kind of question. What am I thinking now? Well, what am I thinking? How might I simplify this going in? About the fraction. What if you reduce? Okay, yeah, suppose I'll reduce it, right? That's a good thing to do. So without loss of generality, I can assume the greatest common divisor are A and B. Right? No harm there. Okay, so it's integral. So we have the following equation. With, I mean, that's basically what it means for A over B to be the root of some monic polynomial, right? I agree. Now, I don't know about y'all, but despite the fact this is an algebra class, I don't like doing computations of fractions. It's really annoying. And there are equivalence classes too, which is totally obnoxious. So I'm going to clear the denominator, so to speak. Now, let us suppose let's suppose that there exists a non-zero prime capacity, right? Because after all, I don't know much, but I know that most of my integers factor in primes, right? And by the way, let me also throw this in, although I didn't earlier, the one integer that I know that B is not is 0, right? B ain't 0. Well, this means if P divides B, then P divides A to the n, right? Because this is divisible by P, and of course so is 0. Right? So 0 is divisible by P, and most of that polynomial is divisible by P because it's all got a factor of B in it, correct? That means that P must divide A to the n, correct? But P is prime. And you actually really do need prime here. So P divides A. And what, pray tell, would be the problem with that? Right. As GCD, AB is 1, this is impossible. So I have but one conclusion to come to, and that is, I know that every integer except for 0, plus and minus 1 are divisible by some prime. So this can't be anything except 0 plus or minus 1. And it can't be 0 either. So B plus or minus 1, because these are the only non-zero integers that are divisible by no prime whatsoever. Hence, A of B is in Z. And Z is going to be closed. You know, doing math is often about copying, right? We see various things, patterns, and we say, can I spread this out into a larger theater, right? Anybody look at that proof and tell me how I can generalize this? What was important in this proof? Was it important that it's the integers, or is it something more general? What's that? GCD. Okay. What else did I use? What is the property of integers? Can anybody say something more general about the ordinary integers that make this work? UFD, right? I mean, that's really it. So actually, we can replace this by saying any UFD is integrally closed. And actually, what you said first is correct as well. Some of you have not heard of this, but we'll get to this later. Actually, this same proof essentially works for what they call a GCD domain. See if you can guess what that means. The GCD domain is actually an integral domain where every two elements have a greatest common divisor. One would think that this is a unique factorization domain, and it turns out every unique factorization domain is a GCD domain. But deep in the depths of some Stephen King novel, there are actually GCD domains that are not UFDs.
That's my question.
Sure.
So if we don't have unique factorization here, what breaks down? Why would this argument work?
Well, you don't need unique factorization because GCD domains that aren't UFDs aren't even atomic. So there are some that can't be factorized. What you do need, here's the problem right here as far as factorization goes. It is possible, if P is an irreducible but not a prime, it is possible for P to divide a large power of something without dividing the thing itself. Right. So that's another potential problem. Okay, I always like non-examples too, to sort of illustrate. Can anybody, by the way, can anybody think of an example of an integral domain? I like domains that's not integrally closed. I'll give you the code. Here's one. And it's actually funny because integrally closed almost seems like I'm desperate to like write definitions down so that you don't fall asleep on me, right? But it turns out that the property of a domain being integrally closed, even though that seems like maybe a little esoteric and off the beat, it's actually incredibly important. Domains that are integrally closed are much more mild-mannered and well-behaved than domains that aren't in general. And domains that are not integrally closed, sometimes if you're looking for strange examples, is a good place to start looking. Let me give you a large class, and then I'll work with a specific one. Let n be a natural number. So, for example, you might have something like Z2i, where the I coefficient is always even, or Z5i, where the I coefficient is always above I, and so forth. So here's an infinite class of family. This is integrally closed. If and only if n is equal to 1. And I can give you short proof of this. This direction, if you're a number theory junkie, you might even know that Zi is a Euclidean domain, as a matter of fact. So it's certainly UFD, and that implies that it's integrally closed. By the way, let me point out that just because you're integrally closed does not make you a UFD. I'll give you an example of that too. Suppose it's better than 1. Okay. Note, if n is bigger than 1, then I is not n. Correct. Because the only way you're going to dig an I out of there is by letting A be 0, and then the only shot you've got is if n is 1, right? Then anything bigger, you're totally toast, right? So I is not in here. However, I is a root of x squared plus 1 right? Because really the only coefficients you need are integers. You don't even need any of this fancy stuff. So if it is bigger than 1, it's not integrally closed. Notice that yeah, this one's not a UFD, but it's also not a GCD domain either, but it's still integrally closed. It turns out, and we'll get to this later, that if you have any domains integrally closed, so it's polynomial ring, for example. Let me give you another good one. This is a ring. It's one of my favorites from factorization. Take a field and look at this. So this notation might be a little bit confusing, but let me point out that once you have a ring that contains, so this is actually a subring of a polynomial ring. Once you have x squared, you have all even power stacks, right? And so you've got x squared, you've got x cubed, you've got x4. Now 2 plus 3 is 5, so you got x5. And now you got everything, because you've got x3, x5, and now you can use that too to make any odd power, right? So this is all polynomials that have 0 for, so in a certain sense, the linear term is missing. So a garden variety element of this looks like A0 plus A2 x squared, A3 x cubed, AK xk, where AI is in field. So this is always missing kind of linear term. Now, let me point out, that this is not notice that X the element X is in the quotient field of this, right? Because it's just this divided by this. However, and is not in, what do you call this? Bring all our stuff on that word down every time. By construction, X is not an R. And X is a root of the polynomial y squared minus x squared. In R. This is a polynomial, all of these coefficients are in R. And yet, and X is the root of it, but it's not the root. So. Okay, any questions on that? Yes.
R Y. Are in the term.
Oh, I'm sorry. Yes, that's very slight. Absolutely. I do. I want my indeterminate here is Y. Thank you. Notice that little professional job of Xing out the X. It made it worse, didn't I? Okay, here is, this is actually a very useful. In like two of my most recent papers, we were talking about atomicity and stuff. This next result was used to help us out on a number of occasions. And it's kind of a simple thing, but it's neat to know about integral. So here. So let R and T be an extension of rings. If T is integral over R, and R in R is a non-unit, then R is also a non-unit. So I call this kind of no new units theorem. Although that's, I don't want to confuse you with me saying this because T can actually, it's a new since you actually have more units than R, right? For example, the interval extension Z inside the Gaussian integers, right? The units in the integers are plus or minus 1. The units in the Gaussian integers are plus or minus 1 and plus or minus I, right? But plus or minus I does not come from the original base ring R. So what this says is you can't turn into a unit by jumping into an interval extension, right? You can't. If you're non-unit downstairs, you remain a non-unit up in the interval extension. Notice that this is very different from localization, right? So for example, when you pass from a ring to its localization, everything in that multiplicative set turns into a unit, right? So there's all kinds of stuff that become units upstairs in localizations, but in interval extensions, it's different. It's sort of dual. So let's prove this. Suppose R and T, I'm sorry, R and R is a unit in T. So what does this mean? So there exists a TNT such that RT as T is an interval extension of R, there exists Ri and R such that Tn plus Rn minus one, Tn minus one, R1T plus R0 is equal to 0. Everybody okay with that? Now, what I want to do here is now I want to multiply by Rn. So I get RT to the n. I'm gonna have an Rn here. I only need n minus one of them to absorb into that. Right, that balances out because I've got an Rn there, right? R1 Everybody okay with that? Now, every RT becomes one, right? RT equals one, so I can suppress all of these, and so what I get is R, or I'm sorry, one, and that's a one, plus R1, R n minus one, plus R0, R n is equal to 0. And now I've totally got this thing, because 1 plus R times Rn minus 1 plus Rn minus 2. So the notation. R1 Rn minus 2 plus R0 Rn minus 1 is equal to 0. Now take this over the other side, and so R inverse is basically equal to this thing, negative which is an element of R. So unit above implies unit below, and so that establishes it. So if R is a unit upstairs, then it had to have been a unit downstairs. So if it's not a unit downstairs, it can't be a unit upstairs. Okay, any questions on that? Let me point out also, and by the situation, I mean where R, T is a ring extension of R, and it's always the case that UR is contained in UT, right? And in fact, this containment can be strict, like in the case of Z inside the Gaussian integer. However, none of the new units come from below. Okay, questions? All right. Okay, so let me give you, this one here, proposition. Whatever the number is, 319. I can just repeat it later in the notes for some reason. I don't remember to skip over it when I come to it again, but this is a silly result, right? So why am I doing it? Because the proof is really easy and it's like, oh my goodness, it's obvious, but this is actually something that comes up and is actually kind of useful. Let R be a commutative ring and U an invertible element of a ring containing R. One and R. So I'm going to U. An invertible element. Before I go on, let me explain why I worded this kind of in a funny way here. Let me give you some context. Suppose R is an integral domain, right? Then what this says is U can be any element of the quotient field other than zero, right? Because take any non-zero element of R, right? R, if R is non-zero, it's invertible in the quotient field, right? And that's a ring containing R, right? So this is really kind of to take and you're going to see what we mean invertibility eventually. So we're just kind of dodging zero divisors here. U inverse, so let me put a period here. U inverse is integral over R if and only if U inverse is in R U. And of course, you can mix and match this, right? So you can say U is integral over R if and only if U is contained in R inverse, is contained in R adjoining U inverse. All right. Let's go through the proof of this. And you know, the proof is when you start to see the proof, it can kind of make you chuckle a little bit because it's essentially straightforward what it is. So let's suppose, first of all, that U inverse is integral over R. Suppose you've got that situation, right? What I want to do is I want to do, I've got lots of big negative power to view here, right? I want to just preserve one of them. So what I want to do here, I guess the biggest negative power that I see is U to the minus n, and this is U to the minus n plus one, this is and so forth. So I want to multiply by U to the n minus one, both sides. And this is going to become U minus one plus the next term is going to be, so that's one minus n, so that's going to be U to the zero. So this is R n minus one. R1 U to the n minus 2, R0 U to the n minus 1. Agreed? And so notice this chunk right here is in R adjoining U, right? Because this is the smallest ring containing all of R and U, and so therefore UN first is in RU. On the other hand, the proof in the other direction is almost identical. So suppose U inverse is in RU, then you basically just kind of build it back, right? So U inverse plus RU of UN minus one. Right, if I use my notation effectively, this is what U inverse and RU means, right? If I choose my indices so that it looks like this, right? Everybody okay with that? And now just reverse the process. And there you go. Right, so the proof of this is not too bad, right? But this will be useful to us. Corollary, I like a good corollary. And this is, I believe that in a roundabout way, I probably asked some of you that actually took 8520 with me. We talked about fields, I probably did something like this. Corollary. Let's let R be an integral domain. And F a field continuum. Maybe the quotient field may be something much larger. If F is integral over R, then R is contiguous. This is a new corollary. So if you have a field that's integral over a domain, then that domain itself has to be a field. And this previous one proof. F is equal over R. And R in F is a unit. All right, and remember, no new units. So since F is an integral extension, R and F is a unit, that since it's a unit up there, it had to have been a unit down there. Therefore, R, because every non-zero element must be a unit. Okay. Questions? Found our way through this one. Let T be a commutative algebra over R. R is a commutative ring. Ring with one and T. Okay, this is yeah, I know where I'm going to need it too. Meaning R alpha. The following conditions are equivalent. Number one, T is finitely generated. T is a finitely generated R module. remember, if you have an algebra over R, in the first place, it has to be an R module, like first and foremost. And so, okay, one of my conditions is I'm gonna say, hey, T, you gotta be finitely generated. This is equivalent to saying that T is finitely generated as a ring over R and T is integral. So T is finitely generated as a ring, and it is also integral over R. Okay. So let's take a look at proof of this. We already have one in class two back in the day, because if T is finitely generated R module, I mean, that's necessarily, then certainly those generators generate T as a ring, and this condition is our integrality module. Because remember, all of T is a generated module, so it's pretty easy to find. You have an integral element, UT is contained in T certainly, right? So no problem in this direction. The interesting thing is if T is finitely generated as a ring, right? And actually, finitely generated as a ring is sort of easier to do because you have more ways to generate. So for example, if you have a ring R, if you look at the polynomial ring, Rx, right? That's finitely generated over R as a ring, right? Because all you need is R and X. But it's not finitely generated over R as an R module, right? Because it's an R module, you need all the powers of X, right? You can't multiply this thing from the module perspective, right? So let's see why 2 implies 1. Suppose T is generated over R by, let's say, T1 up to Tn. And suppose each Ti has minimal monic polynomial and by minimal, what I mean is just minimal degree, just find anything of a minimal degree. With degree, we'll call it Ni, I guess. So, as an R module, T is generated by the set of elements that look like this. T1A1, T2A2, up to T N AN, where each AI, actually, let me call this MI, so there's no confusion here. With each AI NI minus 1. Right. So why does this work? Because what happens is whenever you get to this maximal power, right, then you can rewrite this Ti as lower powers of T, right? That's what the integrality does for you here. So see if you can kind of sort that out and let me know if it doesn't stick. Any questions? Any questions? Well, I hope to see you all at the science picnic. Otherwise, have a great weekend and my trouble will resume next time.